thanks for watching, and today I would like to talk to you about the most important logical connective, P implies Q. For instance, a very standard statement in math that we'll talk about today, for all x in R, x is greater or equal to 10 implies that its square is greater or equal to 100. So P implies Q. And more precisely, you would define P implies Q to be if P is true, then Q is true. Now, the question is, what does a truth table look like? And this is quite interesting. You'll see. So you draw P and Q, and then P implies Q. And you have all the possibilities, true, 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 false, false, true, and false, false. Now, let me explain this to you with a little analogy. Suppose you're signing a policy for car insurance, and the policy maker tells you, if you get into an accident, then we give you $1 million. Now, the question is, when is this not a scam? So when is the policy working? Now, first scenario, you get into a car accident and we give you $1 million. Well, hopefully you agree the policy is working. So if P is true and Q is true, then P implies Q is true. Now, what about you get into an accident, but we don't give you $1 million? Then you might say, oh, I'm angry, the policy didn't work. So in this case, it's a scam, so it's false. Now, maybe more interesting scenario, let's do the fourth one. Suppose, hopefully like most of us, you don't get into an accident and the policy doesn't give you $1 million. Would you say it's a bad policy? Well, not really, because you haven't really been in an accident, right? It's not false that if you're in an accident, then we give you $1 million. So false implies false is true. Last but not least, now that's maybe most interesting scenario. Suppose you don't get into a car accident, but the policy is so nice that we give you $1 million. Would you be angry? Probably not. And in fact, it's still the case that it's not false that if you have a car accident, then we give you $1 million. So kind of by default, this is also true. So here the truth table is true, false, true, true. And I will explain this a little bit more in the end. So it's normal that you're weirded out by this. Just wait a couple of minutes or just fast forward and you'll see a more intuitive explanation. But let me give you a couple of examples of scenarios. For instance, what about the following? Is this a true statement or not? 1 plus 1 equals 2 implies 1 plus 1 plus 1 equals 2 plus 1. Well, by definition, it is true because this is true and this is true. And just be warned, we could give you two random gibberish things. If both of them are true, it's still true. So we can say the Pythagorean theorem implies Fermat's last theorem. Well, both of them are true, but therefore by default the implication is true. But what I wanted to say is, most of the cases it actually makes sense. So it really follows logically from one step to the other. And in fact, you might say, well, this is kind of correct deduction, right? Because you start with 1 plus 1 equals 2, you add 1 to both sides, and you get the end here. So the point is, this is a true thing. Second of all, what if, again, to illustrate, 1 plus 1 equals 2 implies 1 plus 1 plus 1 equals 4. Well, this is true, this is false, and in fact you might say this reasoning is false, right? If you add 1 to both sides, you shouldn't get 4, you get 3. So in fact, just like your intuition tells you, this is a false statement. In fact, I believe this is how computers can check for false things. Okay, now how about false implies true? What about this? 1 plus 1 equals 3 implies 1 plus 1 plus 1 equals 3. Now, here again, you have false implies true. And here's the thing. By what we said, this is not false, right? Because you basically started with just a false assumption. So therefore we say this is actually true, even though it might not be quite true reasoning. However, I want to just emphasize, this is something you actually sometimes use in real life, because I'm sure you had some friend that says, oh, I'm for sure gonna win your lottery. You would say, oh, well, if pigs could fly, then you can win the lottery. So starting with this clearly false assumption, then you win the lottery, and in that logic system, it's true. And it's the same thing here. You say if pigs can fly, then you win the lottery, whether it's true or false. But again, I'll give you another explanation very soon. Lastly, false implies false. What about this? There exists some x real number such that its square is minus 1, implies 1 plus 1 equals 3. And that's just complete gibberish. But again, it's technically not false because we just started from a false step, right? And therefore, this is also true. So those are kind of the 4 different scenarios. And lastly, I really want to emphasize, it seems very weird, but let me give you some intuition as to why we actually require this. Because consider the following statement. For all x, real numbers, x is greater or equal to 10 implies x squared is greater or equal to 100. The stuff I started with. Now, think in 1 second from your head whether you believe this is true or false. Now, I hope you believe this is true. So this is a very important algebraic law. If x is greater or equal to 10, then x squared is greater or equal to 100. So again, stick to your beliefs. So think, it's almost like a magic trick. Think this is true, okay? And please do not change your belief after that. So, now I say, this is true for every x. So in particular, for instance, it should be true for x equals 20. What does that say? It says 20 is greater or equal to 10, implies 20 squared is greater or equal to 100. So 400 is greater or equal to 100. Again, you believe the reasoning is correct. So this should be true. And indeed it is true because you see this is true and this is true as well. But here's the point. We're allowed to choose any x we want. So for instance, let me choose x equals minus 1 or something. Okay? Then, or even better, x equals 1. Then again, this reasoning is true. So whatever I write in this box is true. So what does that say in this case? 1 is greater or equal to 10 implies, I meant to say false implies false, implies 1 squared is greater or equal to 100. So 1 is greater or equal to 100. Again, both sides are false. Okay? But remember your belief. You assume this is correct reasoning. And in fact it is because, well, if it were true that 1 is greater or equal to 10, then squaring it, you get that 1 squared is greater or equal to 100. And lastly, for the other one, false implies true, just choose x to be negative 11 or something, then negative 11 is still greater or equal to 10. And it is true that if this were greater or equal true, then the square would be true. So then 121 would be greater or equal to 100. So in fact, again, in all those three cases, it's correct reasoning, but, for different reasons. Here, this is true, therefore this is true. Here, well, we started with a false promise, but if this were true, we would have had the correct conclusion. So the whole thing is true. And here, well, we started with a false premise, but somehow the conclusion is still correct. So here, false would imply true. And therefore, I know it's weird, but you see, because we basically want math to work, this makes sense, and it also has to do, I think, something with proof by contradiction also relies on this premise. Last but not least, why is this important in math? Again, just like another video I've done, it helps you sort of deconstruct the skeleton of the proof. It helps you figure out what you have to show. For instance, if I ask you to show that if x is greater or equal to 10, then x is greater or equal to 100, x squared is greater or equal to 100, you would always start by saying, suppose x is greater or equal to 10, you do something, and then you would say, therefore, x squared is greater or equal to 100. So, basically, you start, this is what's called a direct proof. 70% of the times you do this proof, where you just start with this and you show this is true. In fact, again, this deconstructing a statement is, again, very important, especially if you have test anxiety. So let me give you one of the most feared statements in calculus, called an epsilon delta statement. And forget about the gibberish for a second. For all epsilon greater than 0, there exists delta greater than 0, such that for all x minus 3 less than delta implies x squared minus 9 is less than epsilon. And as I said, forget about this. And first of all, be scared, okay? Get over it. And then forget about this part for a second. What is this really saying? It's a P implies Q statement. What does that mean? And it is true in this case. It means that at some point in your proof, you would have to say, suppose x minus 3 is less than delta, and then you would say, show x squared minus 9 is less than epsilon. And in fact, if you look at all the epsilon delta proofs, they go somehow like this. You suppose this is true, and you show this is true. So again, kind of deconstructing the skeleton of a proof, and that's why those things are important, but also for stuff like proof by contraposition, proof by contradiction, other fun things. All right, I hope you like this, but if you want to see more math, please make sure to subscribe to my channel. Thank you very much.